Our next speaker is Dr. Thankfila Dayananda. The topic is coconut Coir Pith lignin-based fertilizer matrix for controlled release of urea. The ID is number 3. Dr. Takashia, the floor is yours.
It's a recorded presentation, so I will also play it, but she has a co-host and to join us for the Q&A session. All right, give me a moment.
Please, thank you. Go ahead.
All right, let's share screen. Right, can everyone see again? Yep, all right. Let's start.
Good afternoon. Our research was focused on synthesizing a novel coconut coir pith lignin-based fertilizer matrix for controlled release of urea. These are the contents of my presentation. Starting with the introduction, an effective fertilizer is a fertilizer which maintains a sufficient nutrient concentration in soil for a long period of time, aiding for plant growth. Urea is the most commonly used nitrogen fertilizer with a nitrogen content of 46%. When urea is added to soil, it is readily hydrolyzed to ammonium and subsequently converted to nitrate. But a major portion of nitrogen added to soil by urea is dissipated by different means, leaving less than 50% for plant uptake. This results in a major economic and resource loss, as well as environmental pollution. As a solution to this, controlled release fertilizers are made by reducing the hydrophilicity of urea. This is done with the help of hydrophobic materials, and these are preferred to be biodegradable, non-toxic, readily available, and cheap. The starch urea borate lignin fertilizer is a one such matrix which reduces the rate of release of urea. Starch is a hydrophilic biopolymer which is readily available. Borate acts as a cross-linker between starch and urea, and lignin acts as a plasticizer, increasing the hydrophobic nature of the matrix. Lignin is a complex phenolic biopolymer built by random cross-linking of 3 major phenyl propanoid units. Structure and properties of lignin highly depends on factors such as the species, location, season, age, etc., and on extraction methods and conditions used. There are a lot of favorable properties of lignin which makes it an ideal raw material for controlled release fertilizers, but there are challenges to overcome as well. Therefore, lignin is combined with other suitable materials as in this research. In our work, instead of using commercially available lignin, coconut coir pith has been used as the source of lignin. Coir pith is a byproduct of the coir industry, which is plentifully available in Sri Lanka with a very low industrial value. Coconut coir pith has a high lignin content of 33%, and the coconut coir pith lignin hasn't been used for controlled release fertilizer preparations or any other research applications. So, the aim of our research was to synthesize an effective fertilizer for controlled release of urea by incorporating lignin extracted from coconut coir pith into the starch urea borate lignin matrix. To achieve this, the following objectives were fulfilled: extraction of lignin from coconut coir pith, characterization of lignin, preparation of the fertilizer, Urea release studies and optimization and characterization of the fertilizer. Moving on to the methodology, lignin was extracted under 4 main protocols with minor changes in the experimental procedure, and a number of lignin samples were obtained. In acid protocol using sulfuric acid as the key reagent, lignin A1 and A2 were extracted. The second protocol is a modification of the first one, in which a solvent extraction using acetone is done prior to the acid hydrolysis to obtain lignin B. Sodium hydroxide was used as the main reagent for protocol C to obtain 3 lignin samples, while a mixture of acetic and formic acids were used for organosolv protocol to obtain lignin D. And by characterization, lignin A2 and C3 were selected for the preparation of the fertilizer. This is the procedure for the one-pot synthesis of the fertilizer, and masses and types of lignin used are indicated in this table. Here, the fertilizer film without lignin is used as the control, and different lignin contents were used to confirm that 10% lignin is the optimum content. Next, release studies were carried out by photometric determination. A constant mass of the fertilizer in a dialysis tubing was placed in water, and the absorbance was measured by withdrawing samples at regular time intervals. Let's move on to the results and discussion. Characterization of lignin was done by FTIR spectroscopy. Out of the lignin samples obtained by acid protocol and the modified acid protocol, lignin A2 corresponds the best with the literature spectrum. Here, the band positions are compared and interpreted. In the case of alkaline protocol, lignin C3 corresponds well with the literature spectrum of alkaline lignin. Here too, the values were compared and the bands were interpreted. Similarly, the FTIR spectrum of lignin D was compared with the literature spectrum and the bands were interpreted. By FTIR analysis, lignin samples A2, C3, and D were selected as the representative samples of each protocol, and their particle sizes was analyzed by particle size analysis. Lignin C3 possesses the smallest particle size with a distribution well within the nano range with a D50 value of 11.9 nanometers. Lignin D also has a D50 value in the nano range, while the largest particle size is observed in lignin A2. Also, the percentage yield of each lignin sample was calculated, and out of the representative samples, lignin A2 and C3 were selected for the fertilizer preparation. This was considering the economical factors. Now let's move on to the release studies and kinetic modeling. The graph compares the release behaviors of pure urea and the fertilizer films. For pure urea, a burst release of 92% occurred within 30 minutes and an almost complete release occurred within 90 minutes. For the SUB film without lignin, a fast release of 60% occurred within 75 minutes, and the rate of release decreased, overall releasing 73% of urea in 5 hours. When lignin is incorporated into the matrix, the release rate has been reduced further. For SUB-LA2 and SUB-LC3, a gradual release of around 70% occurred within 5 hours. In both cases, the release was smooth and no burst release was seen, unlike in pure urea and SUB film. Within the first 75 minutes, 52% of urea was released from the SUB-LA2 film, while in the case of the SUB-LC3 film, it was a much lesser value of 42%. By comparing the complete release profiles of the two films, it can be seen that the SUB-LC3 film shows a much efficient controlled release behavior compared to SUB-LA2 throughout the graph. Especially at the start of the release, SUB-LC3 clearly shows a slower release rate with a lower slope compared to SUB-LA2. It can be suggested that the high efficiency of the SUB-LC3 film compared to SUB-LA2 film is due to different extraction protocols of lignin, LA2 and LC3. The release profiles of pure urea and the best fertilizer film were obtained by carrying out 3 trials of each, including the synthesis of the fertilizer. Release behavior of the SUB-LC3 film shows a higher error and hence a lower reproducibility. This suggests that the synthetic procedure may not be appreciably reproducible, and also the heterogenic nature of lignin could be a reason for this. Further, by the release profiles of fertilizer films with a lignin content of 5, 10, and 15%, it was confirmed that the lignin content of 10% is the optimum content. Release behavior of the best fertilizer film, SUB-LC3, was fitted into a number of existing standard drug releasing models, but it does not fit any of those models with a significant accuracy. Therefore, curve fitting was attempted to study the release kinetics. The complete release profiles followed an exponential function of the following form, while the first 75 minutes of release was successfully fitted into a linear function. Let's look at the characterization of fertilizer films. By studying the FTIR spectra and the PXRD patterns of individual raw materials and the fertilizer films, the successful formation of the fertilizer can be confirmed as evident by the overlapping of the signals. Also, it is suggested that the fertilizer films formed are amorphous in nature. When studying the SCN images of the transparent SUB film and the best fertilizer film, it was observed that there are rod-like structures in the SUB-LC3 film, which can be due to lignin. So, to conclude, the starch urea borate lignin matrix prepared using coconut coir pith lignin is successful as a controlled release fertilizer with the potential to be developed into an economical industrial scale fertilizer. And as future projections to this study, the release behavior of the fertilizer in soil can be studied, and it can also be continued to perform on-farm field trials. These are the key references that we have followed. Thank you very much.
Thank you, Dr. Dayananda. It is really a very fine research. And I have one comment only. Is that slow release or is it control release?
Hi, so it is called controlled release because when it's slow release, we cannot control the speed, but when it comes to controlled release, we can control the speed at which the urea is released. So yeah, it's called controlled release.
And do we expect if we apply this urea coated with lignin, how long it will stay in the soil?
Sorry, can you please repeat the question?
Yes, when you coat the urea with this type of coating, how long it will stay in the soil?
Actually, we haven't done any work in the soil. We have only used water, but in soil, it will probably last a much longer time because in water, pure water, it lasts for about 5 hours. So in soil, only the moisture is present. There's only a little amount of moisture. So it will be in the scale of days, maybe weeks to completely release the urea. Yeah.
Okay, if we compare formaldehyde urea and this lignin coated urea, which one you prefer?
I think because when just urea is added to the soil, it completely release, like it goes up to 100% within a few minutes. So when compared to that, lignin coated urea is much more effective, and it has other effects as well because it acts as a humic acid precursor. Lignin acts as a humic acid precursor, hence increasing the fertility of the soil, and it is biodegradable and environmental friendly. So yeah.
And you can consider it as a green fertilizer, actually, because it is environmental friendly product. Thank you very much. Is there any other question, Dr. Ramzi?
I think no question. Any question?
Yeah.
Maybe
then let us